Now, let's first have a look at one of the major category of phytochemicals known as phenolic compounds. Phenolic compounds are secondary metabolites synthesized through the shikimic acid and phenylpropanoid pathways. All phenolic compounds contain at least one aromatic ring with one hydroxy group in their structure and can be classified into two main groups known as flavonoids and non-flavonoids. In this session, I will explain the diversity of flavonoid structure because flavonoids are the most abundant phenolic compounds in fruits and vegetables. They account for nearly 2/3 of dietary phenolic compounds, and as a group, they are the most bioactive. Flavonoids contain a phenylbenzylpyran skeleton. Two phenyl rings join through a heterocyclic pyran ring. Flavonoid can be divided into 6 groups according to differences in the pyran ring. The most basic structure of flavonoids is flavones. They contain a keto group in carbon 4, a double bond between carbon 2 and carbon 3, and a B ring is attached to carbon 2. The most abundant flavones in fruits and vegetables include apigenin and luteolin. Isoflavones are flavones in which B ring is attached to carbon 3 instead of carbon 2. This structural feature makes isoflavones resemble estrogen, female sex hormone, so they possess mild estrogenic activity and are known as phytoestrogen. Isoflavones are abundant in soybeans and many soybean products. They are also present in low amounts in other legumes such as beans and peanut. The main isoflavones are diazine, genistein, and glycine. The third group of flavonoids is flavonols. Flavonols are the flavones hydroxylated in carbon 3. They are some of the best antioxidant flavonoids due to their pattern of hydroxylation, where the hydroxy in carbon 3 is thought to increase the stability of the flavonoid radical form. Once the compound has acted as a radical scavenger, flavonols are the most abundant flavonoids in fruits and vegetables. The major flavonols are camphorol, quercetin, and myricetin. The fourth group of flavonoids is flavanones. There is no double bond between carbon 2 and carbon 3 of ring C of flavones, but they possess the keto group in carbon 4. Major flavanones are naringenin and hesperetin. They are found in citrus fruit and some herbs like oregano and peppermint. The fifth group of flavonoids is flavanols or flavantriols. Flavanols are lack of the double bond between carbon 2 and carbon 3 and the oso group in carbon 4, but contain an hydroxy in carbon 3. The major flavanols are catechin, epicatechin, gallocatechin, epigallocatechin. They are polymers and oligomers. Oligomeric flavantriol are called proanthocyanidins, while polymeric forms are named condensanin. Epicatechin and catechin are the most widely distributed flavantriol and can be found in many fruits like grape, strawberry, apple, and fruit juice. So, now we look at the last group of flavonoids compound, namely anthocyanidin. Like flavantriol, anthocyanidins do not present a keto group in carbon 4, but possess an hydroxy in carbon 3 and 2 double bond in ring C. Due to this structural characteristic, they are the only ionic flavonoids. The basic skeleton of anthocyanidin is the flavillum cation, which gives these flavonoids with unique properties. They constitute the largest and probably the most important group of water-soluble plant pigments. Anthocyanin are abundant in berries, but they can also be found in color fruits like grapes, cherries, and plum. Almost all anthocyanins are glycosylated derivative of 6 anthocyanidin, namely pelargonidin, cyanidin, daphnidin, peonidin, petunidin, and malvidin. As summary, we have discussed on one of the major categories of plant-based bioactive food components, which are phenolic compound, or more specifically flavonoids. Therefore, through this video, I hope that you are able to gain a general understanding of classification, source, and structure of flavonoids. Thank you.